All right, so in 1.4, I have your assignment at the top here, just so you know, make a note of it. And in 1.4, we're looking at our first actual kind of technique, or one of the techniques for solving differential equations. And so we're going to kind of expand on things that you've maybe seen in the past, particularly in 1.5 and 1.6, but this is kind of our first branching off. In 1.2, we looked at differential equations that just were dy dx equals fx, f of x, a function of x. And then we looked at both general solutions where you still have a plus c somewhere, and particular solutions where you've used a set of initial values. In 1.4, we have a new type of problem where we're looking at differential equations that are the form dy dx equals, and now what's on the other side is both a function of x and of y. And in this first section of this, or in 1.4, we're looking specifically at situations where these differential equations are separable. A separable first-order differential equation is one that we could write, even if it starts this way, we can manipulate it algebraically so that we can write a function of y on the left times dy dx equals g of x. And then we can actually solve by integrating both sides. So what we kind of end up doing is we end up with f of y. I said y and then I immediately wrote x. Let's try that again. Dy equals, and then g of x dx is kind of the idea. We're going to integrate the left side with respect to y and the right side with respect to x. And when we integrate those, we end up with some new function of y, technically plus c equals some new function of x, also plus c. And basically what we do is we're not going to have constants on both sides that are arbitrary. We would essentially subtract one side over, and usually we group the constants with the side involving x. So that's going to be the idea. We're going to separate all the y stuff on one side, all of the x stuff on the other, and then integrate both sides, and then have our solution, or maybe do some initial values from there. So let's look at this, and we're going to get a general solution first. And we're going to look to write it as an explicit solution. An explicit solution means after we do everything else, we are going to solve this so that it's y equals as our final solution. So in this case, I have dy dx plus 2y squared times x. So the first thing I'm going to do is subtract . So the first thing I'm going to do is subtract the 2y squared x from both sides so that I end up with dy dx equals negative 2y squared x. So now I'm not adding or subtracting, I've got my two pieces here, and then I'm going to divide on both sides by y squared. And then I'm also going to multiply by dx, so that'll make the dx go to the other side. So then what I end up with, on the left I'll have dy over y squared, or some people like to rewrite it for integrating purposes. Instead of dy over y squared, you could write it as y to the negative second power times dy equals negative 2x dx. Once I have that squared away, then now I am going to integrate. So now if I integrate on both sides, when I integrate on the left, I'll end up with a negative y to the negative 1 power, technically plus c. But on this other side, when I integrate negative 2x, I end up with negative x squared plus c. So the constant of what I got on the left, I'm just combining over on the right. And they were both generic constants, so I still have a generic constant. So right now I have negative 1 over y equals negative x squared plus c. This is a solution, a general solution. However, it's not explicit yet. If I want to make it explicit, I need to solve for y so that it's y equals. And I could multiply by -1. So that would give me 1 over y equals positive x squared minus c. Sometimes in textbooks you'll see, because this constant is still arbitrary, they might not even bother changing the sign in between or changing this to a negative c. We haven't committed to any initial values yet, but I'm just going to write minus c. And then I need to take the reciprocal of both sides, or if you wanted, you could think of putting that over 1 and cross multiplying. Either way, what we would end up with is y equals 1 over the quantity x squared minus c. And that would be my general solution, because it still involves a constant, and it's a general explicit solution because I have it solved for y. Next, I can take that same solution, so I'm just going to start right where we left off. And if they gave us an initial value, we can solve to find the constant. So in this case, my y would be -2. X squared is really 1 squared, and then minus c. So -2 equals 1 over 1 minus c. This is a case where maybe you probably do want to cross multiply, but handle it how you'd like to. This would give us -2 plus 2c equals 1, which means 2c equals 3, which means that c equals 3/2. So then once I have my constant, I can now write my particular solution, which would be that y equals 1 over x squared minus 3/2. So that's our first separable equation and a particular solution of that separable differential equation. Okay, so let's try another one. This one's already kind of rearranged to make things a little bit smoother. So right away, right off the bat, I'm just going to divide by y on both sides, and I'm going to multiply by dx. So I end up with 1 over y dy equals -6x dx. And this time when I integrate, I'll end up with the natural log of y, which should have absolute values around it, absolute values around it, equals -3x squared plus c. Now the absolute value bars we're going to talk about in a minute. There's different ways that different books handle these, and I've kind of done a lot of digging around to try and find out the best way to handle them. We'll talk about in class how we're going to handle them. Right now, for this particular problem, we can, because of the initial condition, I know that we're dealing with positive y's near 0. So I really don't need to worry about the absolute, or I can drop the absolute value bars because I don't need to worry about that negative case. And then so this would be a general solution. If I want an explicit one, I just need to make this an exponent, or raise both sides to be powers of e. That would give me y equals e to the -3x squared plus c. And then a common trick that I think you guys see in calculus is I'm going to use exponent properties in kind of in reverse of what we normally do. Normally we want to combine exponents. I want to split it apart and say e to the -3x squared times e to the c, because now this is just a different constant. E is a constant. I'm raising it to the power of an arbitrary constant that I haven't committed to or tested or used any values for yet. And then often that will be used, sometimes books will use an a. For me, I'm just going to stick with, I still have an arbitrary constant c, and then e to the -3x squared. So this is going to be kind of a common trick that we see when you get e to the -3x squared plus c, or e to the something plus c, that we're going to end up with that constant c out front because of the exponent property trick, and then whatever the rest of your exponential piece is. So that takes care of just solving and getting our general solution, but we did have an initial condition here that when x was 0, y was 7. So then we have a 7 over here e to the negative 3 times 0 squared, but that really just means that we have c e to the 0, which really just means we have c. So our constant is 7. So my particular solution in this case would be 7e to the negative 3x squared. The only thing we need to be careful about is we did switch this to be a new arbitrary constant c, but then once I use that as kind of my general form, when I find that constant, it's this c. I can't go back earlier and put it in the 7 up here. I would have to solve that a totally different way and put in the 0 here and the 7 over here. But anyway, so this is our final particular solution. So then the question comes up. So this is the same situation. It's the same original problem. But what if we had a different initial condition? And in this case, we're going to address this absolute value issue. What if instead our initial condition had a negative y value when x was 0? And over on the right I have the slope field, just so you can see it. And up here was the solution we just looked at. Now we're looking at a solution down here and trying to figure out what happens. Well, what ends up happening is now we can see, because of the value they gave me, that I know y should be negative. So I really should have a negative y in here. And if we went to go manipulate from this point, from that point where we had the natural log of absolute value y before, if we go from here and we make both sides powers of e, like we did before, we end up with negative y equals e to the negative 3x squared plus c. We can still do our same, okay, we're going to fill in a negative 4 for y. And this, using the same trick we had before, would become c e to the negative 3x squared, just like we had before. So then we'd have c e to the negative 3, which really means that c ends up being 4, because we had the negative 4. And so you end up with negative y equals 4e to the negative 3x squared. But then if we solve for y, we end up with y equals negative 4e to the negative 3x squared. And so part of the point I wanted to show you with this is that ultimately it's not going to matter with the absolute value piece. Let's say we didn't do that. So just to emphasize that this is a different scenario. Let's say I didn't do this whole, let's assume it's negative. Let's say I just plowed ahead like before. I'd never worried about the absolute value bars, and I just started from this point. And we did our e to the power of, so then I have y equals ce to the negative 3x squared. And then I said, okay, I'm going to use this new initial condition, and they tell me when x is 0, y should be negative 4. So when x is 0, y is negative 4. So then all of this still becomes 1, so you end up with c. So now we have c equals negative 4. But this time I was starting with kind of a slightly different equation. So when I go back, I still end up with negative 4e to the negative 3x squared. Well, that's the exact same thing we got the other way. So part of the point of this, and I'll show you another thing in class if I haven't already, depending on when you watch this, of a professor who kind of made a big post online and kind of said, this is what I do in my differential equations classes. And we're going to take the same approach. We are not going to worry about the absolute value bars on y. It still is there. It's something you should keep in mind when you get, if you take another class again, start by doing it. But in a lot of answer keys and a lot of different textbooks and in a lot of notes of professors, they kind of blow right past the absolute value bars. And at first I didn't just like doing it for no reason, but now that I've kind of seen it, one, seen it in so many places, and two, seen that post that we're going to talk about in class, I kind of feel better just saying, you know what, we're not going to worry about it. Let's worry about the techniques and not the nitty-gritty of the absolute value, because in almost every practical case, the initial values and the problem itself take care of the issue. So, just a couple more examples that I want to do, and then we'll wrap it up here. First, find the explicit solution, or explicit particular solution to the initial value problem. If you want to try this one on your own first, and then come back and just check my answer, then you can go right ahead, or you can follow along. Kind of like we did before, we're going to move that to the other side. So then dy dx equals negative 2xy. And then I'm going to move my y's to the left, my x's to the right. And then integrate. So then the natural log of y equals negative x squared plus c. And we will make them exponents here, raise both sides to be powers of e. And then we start with this, but by using that same trick, and I'm not going to work through this every time, hopefully you're familiar enough or that you get used to this, then that we're going to call a constant because we haven't committed to anything yet. We have no initial values. We've started, whoops. So here is my general solution. And then with my initial values, when x is 1, y is negative 2. And the only thing we need to be careful of, that negative was out in front of x. So we end up with a 1 squared is 1. So this really becomes ce to the negative 1. And that equals negative 2. So then our constant, e to the negative 1 is really 1 over e. Our constant ends up being negative 2e. And so then my final, when we look at our solution, coming way back from up here, so y equals negative 2e times e to the negative x squared. But we can do a little bit better than that, because this is really e to the first times e to the negative x squared. So my final solution is I can write as negative 2e to the negative x squared plus 1. And we'll see some things with exponents like that. That's just one to mix that one in there. So this is just more because of the constant being e. There's a slight difference in what happens in our final, to write our final solution. All right, then last example, and there's something a little bit different that happens here just because of the nature of the problem. But we are going to look for a general solution and a particular solution. And this one's already pretty geared up for us to do this pretty well. I can just multiply both sides by 3y squared minus 5 and by dx. And so I kind of do the same trick here, moving all my y stuff to one side and my x stuff to the other. And we're already geared up to integrate. And when I integrate, I end up with y to the third minus 5y, technically plus c, but we're going to move the constant over. And then 4x minus x squared, and this is where both of my c's are going to get lumped together. The catch with this one is I cannot solve this for y. I have a y cubed and I have a y. So this is as good as we can do for the general solution. It's called an implicit general solution because I can't explicitly solve it for y, but this still works as a general solution. And then for the particular solution, I do the same thing. I fill in 1 for x and 3 for y. So then I end up with 27 minus 15 equals 4 minus 1 plus c. 27 minus 15 would give me 12. So then you end up with 12 equals 3 plus c, which means that c is 9. So the best I can do is an implicit particular solution, which would be y to the third minus 5y equals 4x minus x squared plus 9. So that's my explicit, or no, sorry, that's my particular implicit solution. There's my particular general solution. That wraps up notes for 1.4. Certainly if you have questions, let me know. That first book assignment at the beginning of the notes is due next Wednesday.